start the show. Say hello, officially. Happy Thursday. It's not garbage day, at least for me, but it is Thursday. Let's see, things that are happening. Homework 5 is due Monday. I have office hours next week as usual if you need assistance. Also, you can email me. I do check email over the weekend when I have an assignment due, because I figure that's the only fair thing to do. So if you get stuck on something or if it won't run, please let me try to help. You can also have Vladimir try to help. Office hours Friday mornings,
Yes.
Is that right? Friday and Monday mornings. So trying to catch any of those last minute questions. You do get a chance to revise it. It just has to be 3/4 complete with respect to the points attempted for me to take it. And the reason I have that caveat is because one time I had a student who submitted their first draft as a blank piece of paper because they knew that they could revise it. That way they wouldn't lose any late points, and I thought that was not the intent I was going for. So it has to at least be an effort that I can grade to be able to count as a first draft, but it does not have to be perfect. And if you get stuck on something or you're not sure what to do and you want to leave a comment for me, to prompt me for a specific question, that's fine too. You can think of this as a dialogue. Learning how to revise your work in response to other people's feedback is a very critical skill. It shows up in manuscripts, it shows up in grants, it shows up in teaching, it shows up in administration, it shows up everywhere. So it's good to get some practice in how to do that. So let's see then. We were talking about how to set up multivariate analyses in univariate software to start with. You would do this in situations where you're thinking about variables as either predictors or outcomes, but not both. And in situations in which the outcomes are allowed to be correlated and you're not interested in predicting one from the other in a directed path kind of way. So there are two different strategies in terms of how you would specify the fixed effects in these types of multivariate analyses. So I wanted to go back over them since we covered them at the end of class on Tuesday and then show you how it would work in an example. Sound like a plan? Yes? And as an update to the shoelace saga, we have not made much progress. He did wear his new shoes to school yesterday and he came home with them untied, and apparently they had been that way most of the day. And I wanted to also say that I made a joke last time about saying shit in front of my kid. I try not to do that. I'm not a bad mom. I was just going for hyperbole for comedic relief. So he has learned certain swear words from us, but we try very hard not to say them. We try to emphasize the idea that some words are appropriate at school and some words are not appropriate at school. That is probably true for most grown-ups as well. So, for instance, when I give conference presentations, I try not to swear in them. Pro tip, right? When I write a manuscript, try not to swear in the manuscript. But if I'm keeping it real in my classroom, yeah, sometimes it slips out. So, anywho, hopefully by next week I can report some progress on the shoelace tying adventure. Slide 30 is where I am here. So we're working in the type of data where we have multiple outcomes from the same person. We have reshaped the data so that all of the outcomes are in one column. And then we have a new predictor variable that keeps track of which outcome is which. So in that situation, here's the notation that I'm using. I have a categorical indicator variable like DV as to whether it's A, B, or C. So this is a generic example, obviously. And I also used that generic categorical variable to create dummy codes that work as switches to indicate which row the outcome is in. So DVA is 1, we're talking about that row. If that's not DVA, then the other ones are 0. So the two ways to set up the model depend on whether you have a general intercept in the model or not. If you do, which is everything we've seen thus far has started off with a general intercept, the empty model only has an intercept. If you set it up this way, then one of your outcomes is going to be the reference, and all of the fixed effects pertain to that outcome. The fixed effects for the other outcomes have to be linear combinations then. So what the model is going to tell you is what happens to the reference and how each effect you specify differs when it predicts the other outcomes. Thank you, Zoomers. Forgot the screen share again. At least I said what slide number I was on. That's a small victory. All right. Thank you, Zoomers. That should be better. All right. So general intercept, reference outcome, and then differences to each of the others. And you would have to ask for what the actual effects would be for the others as linear combinations. The other strategy, which is more, I think, more intuitive once you get used to the idea, is to use these dummy codes as switches for the intercept and for every single effect in the model. Then there is no such thing as a main effect anymore in this DV-specific parameterization. Everything is attached to a dummy code. So then it directly tells you what happens for each outcome specifically, and if you want to contrast the effects across outcomes, then those are linear combinations instead. So any one model can only give you some of the information directly. The rest of it is available as a linear combination. So we did that slide before. I'm going to skip that for now. So if we have a general intercept parameterization, an empty model, which I still say is empty, because all this is doing is allowing each outcome to have a different mean as a different starting point. So to be parallel with what we would do in a univariate analysis, this would be, these variables are not really predictors. They're just switches that allow each outcome to start in a different place. So given the coding scheme here, reference for the outcome is the third outcome, dv equals c, because that's when dva and dvb would be 0. And so that means the intercept is for c. Beta O1 is going to capture the mean difference of how A differs from C. Beta O2 captures the mean difference of how B differs from C. If you want to know what the mean is for A and what the mean is for B, you have to add the intercept to each of their slopes. So those are the two linear combinations that you would have to make for that. Likewise, if you wanted to know if A and B have different means, you could contrast those two slopes to find out the answer of that. So there's 3 things that the model is going to give you directly. The other 3 are indirectly. If I add a slope of a predictor, generically x here, then the same rationale applies. Beta 1O is the slope of x when the interacting predictors are 0. So given this coding scheme, that means beta 1O for the slope of x is specifically for the third outcome, because that's the only time the rest of this stuff would drop out. Beta 1,1 and beta 1,2 tell you how the slope of x differs for the A outcome than the C outcome, and how the slope of the B of x differs in the B outcome relative to the C outcome. So differences between outcomes is like the key element that this model is giving you directly. If you want to know what the slope of x is for A or is for B, we have to add what it is for C, the beta 1O, and add to it beta 1,1 or 1,2 to get to what it is for each of these things. So the math is what I'm saying is right down here. So again, 3 things you get directly, 3 things that are indirectly implied as linear combinations. So when would you do this? In repeated measures ANOVA types of designs where you're thinking about your within subjects factors and you're interested in looking at how things change across the levels of your manipulation or the types of outcomes that you have. But you're thinking about them all sort of as one thing with just different flavors. So the example that I gave in class, which is one of the examples I linked to on the course website that we're not going to get a chance to talk about, was looking at body image in men and women. And there was a figure of, I think it's from 1 to 10, and people were asked, okay, what is your ideal body type? Like, which of these people would you like to be? And then which of them do you think you currently are? And the whole point of the analysis was to look at the discrepancy between what you think you are and what you want to be, and whether gender was related to the size of that discrepancy. Spoiler alert, yes it was. There was a bigger discrepancy for women than men in the study. So this is the type of setup I would do for something like that, because the idea of having a reference DV and then having the differences to the others, that difference directly maps onto the idea of discrepancy. That's what it represents. So anytime that you're interested in a different score type of outcome, I would set it up this way. So questions on that so far? Oh, cool. Moving on. here's what it looks like in code. And I have the Sass code in here because I know a few of you are still trying to work on Sass. Who's my Sass people? Woo! There's like 2 of us. I love Sass, and you can't take it away from me. Here's Stata. So in this setup here, Y holds all 3 outcomes in one column. So that's my generic column name. And I called it Y because there's no better name for it, right? It's holding 3 different things. I have my DVA, DVB, X, DVA by X, and DVB by X. So these then are, the fact that C is not here means I know that is the reference for this. I would have to decide what kind of relationship I want between the outcome residuals. This is a normal type of model, not a generalized model. And in Stata, the code looks relatively the same in terms of the fixed effects. The rest of this we'll talk about in a little bit. And this is what it would look like if you used a factor variable instead. So if you treated DV as a categorical predictor, so in Sass it would be on the class statement. In Stata it has an I dot in front of it, and in R it would be factor variable as well. So here's the corresponding R code that would go with those ideas. We are going to be using a function called GLS, which stands for generalized least squares. You probably used that before in some of your other classes. And I have a 1 here. What does the 1 represent? Say it louder. Intercept, yes. Now I'm making a point of that because this 1 is going to go away in a minute. But it's still here for now because this is the general intercept version where there's a reference DV and everything else tells you about the differences relative to that reference. So here's the other alternative. In the empty model, I don't have a beta 00 sitting all by itself. It is now attached to DVC specifically. That means that beta 00 does not contribute to the rows where I have A's and B's. In the previous version of this, let me scroll back again, beta 00 would contribute to every single row because there's nothing that turns it on or off, so it's a constant, literally, the constant in the model. By attaching the DVC dummy code, then each of these is specific to that outcome only. And they're shut off, turned off to 0 when it's not that row. So the interpretation here is very direct. This is the intercept for C, this is the intercept for A, and this is the intercept for B, the end. So the 3 things you get directly pertain to the 3 outcomes. If you want to know differences between the outcomes with respect to their means, then you have to ask for those 3 differences. So still 3 things you get, 3 that are implied. We're just switching which 3 they are. If I add a predictor, then note that beta 1O here that used to have just X next to it has DVC on it as well. So then the interpretation is similarly parallel. Beta 1O is the slope of X on DVC. Beta 1,1 is the slope of X on A. And 1,2 is the slope of X on B, the end. If I want to know if the effect of X differs, if I'm predicting A versus B, like if X is a stronger slope for one of my outcomes than another, then I have to ask for those differences as linear combinations. So this version of the model is directly analogous to what happens in path models. Like we just have separate outcomes, they each get their own stuff, they can be predicted by whatever you want, and you don't have to do any sort of convoluted logic to get back to what the alternative outcomes would be. So this is what it looks like in Sass and Stata first, and I've underlined the important part. No int and no constant. What do you think that does? These are softball questions. Say it louder. No intercept, exactly. So this is shutting off the column of 1s that you would normally think of as the intercept that applies to all the rows, and everything now is DV specific. No constant is the same thing as no intercept. In Stata, there are 2 different no constants in the code, though, which gets tricky, but they're shutting off different things. We'll talk about that in the example. Here's if it were using a factor variable instead, what it would look like. Very similar in structure. Again, the no int or the no constant is the critical thing. In R, I was like, how do I take away the 1? Well, what if I just make it a 0? It worked. So how about that? No int is the literal 0 here. So then your model has just these 6 fixed effects in it. So pretty cool. It is possible to mix and match across these 2 different ways of setting up your model, but it can get very tricky to do so. So I would probably encourage you, when you're first trying to do these things, to stay consistent using one or the other. But just as an example of what this might look like, let's say that what we want to do is retain separate effects of an x1 as a predictor for all 3 DVs, but I only want x2 as a second predictor to predict A and B. So what if x2 is not relevant for C, right? I don't want to have that slope in the model. I can do that. So in the general intercept version, it would look like this. So beta 0 is not attached to anything, so that's how I know it's a general intercept that applies to everyone's scores. So this would become the intercept for C. Then the next 2 are the differences in the intercept for the other outcomes. Likewise, beta 10 is the slope of x1. Because of these interaction terms, it's specific to C. The beta 11 and beta 12 interaction terms tell you how different the slope of x1 is for B than C and A than C. But then this part. So there's a hole here that I left deliberately spaced this way for a reason. There is no main effect of x2, but yet I have interaction terms with x2. Now that looks wrong, right? Like you're told if you have an interaction, you have to have both main effects, right? It's because this isn't really an interaction. I think of this as a switch. So what this does is allow this beta 21 slope to only describe how x2 relates to the A rows, and this one describes how the x2 slope relates to the B rows. And there's no corresponding term for how it relates to C because I didn't want that. The same last row is shown down here in the DV-specific intercept version, but the interpretation of everything else is different. So this is the intercept for each outcome, this is the slope of x1 for each outcome, and then this is the slope of x2 for the outcomes for which I wanted them. So this type of coding scheme can also help you set up nested effects when predictors logically do not apply to some people. So for instance, if I had something like a number of children you've given birth to, and my sample included people of all genders, well, biology says that not everybody has a chance to give birth. So that question logically only applies to the people who could possibly do so. So I might have something that looks like an interaction term where I would have the predictor of how many times have you given birth, and then the switch variable would be an indicator for 1, you are biologically possible to do so, or 0, you are not. So then that slope only applies to the people that it's possible for, and it doesn't apply to the people that it's not possible for. Likewise, if I had something like the severity of a disease, and not everybody has the disease, then I would do something like this. If you have it, is the indicator variable for the switch here, and then the slope for severity would only apply to people for whom the disease is active. So this can be a way to address missing data or unknown data. Nested effects is sort of a general concept, and we're using that strategy to be able to create outcome-specific prediction in a multivariate analysis. All right, so there's my summary. Questions so far? Yeah.
Those for both generalized and general, like just are those for both categorical outcome and continuous outcome?
Yes, because this is only focusing on how you specify the fixed effects, and that is agnostic as to what kind of model it is. So there's only one example in which I think you can't do the DV-specific one, like in SAS, if you have an ordinal outcome, it won't let you do this. It won't let you kick out the intercept. I'm not sure if the other programs do that too, but otherwise it shouldn't matter. You should be able to do this regardless. All right. You want to see an example? Why not? I don't think anyone's ever said no to that. Examples always help. All right, so these are real data in this example, which is why they're not in the download folder. They are from my Penn State days when I was in the Human Development and Family Studies program as a postdoc and then teaching these classes for the first time. And in that type of research, it's very common to survey multiple people from the same family with respect to their family dynamics. So this is a study actually of adult families. The setup is that they recruited people who are in heterosexual relationships, still married, and at least one of their adult children. So it's an adult child and their even more adult mom and dad. The adult children were coded as either men or women. And the outcome that we're predicting in these 140 families is the scale mean of a measure of gender roles in which higher scores indicate more conservative attitudes. So questions like, a woman's place is in the home, yes? Those kinds of things. Not quite that egregious, but possibly along the same lines. So more on this scale means more conservative, more traditional, how you might want to say. The example predictors are the gender of the adult child and the level of education of each of the family members in years of education, which I have centered so that 0 means a high school degree. So you might look at this and think, okay, I'm going to predict attitudes from one variable of gender and then each person's education. How complicated could this be? It doesn't sound like a lot, but it can get big very quickly. In this example, we are going to use an unstructured R matrix. So that word means everything gets to be what it wants. We're just going to let the residual variance for each person be different for the moms and the dads and the kids. And we're letting each pair of residual correlations be different as well. So we're not putting any assumptions, any structure on this. I have 140 families and only 3 outcomes each, so this is a reasonable thing to do. Do I have to have complete data? Could I include families that had only the mom and not the dad? For instance, theoretically? I could, so long as I'm using likelihood estimation, I could. If I were using ordinary least squares in a traditional multivariate analysis of variance kind of thing, or a traditional repeated measures ANOVA kind of thing, then I would only be able to use families that have all 3 outcomes. So we can use partial data to maintain whatever power and inference that we can. In this case, I believe I deliberately filtered out any missing data just to keep all of the ends the same. Let's see. So I'm going to show you first the empty model using the general intercept versus the specific intercepts, and then we'll focus on just the specific intercept versions. In part 1, we're going to do this analysis using the traditional univariate software, and in part 2, we will look at the same models as path models instead, so you can see what the translation is between how you know how to do things and how you soon will know how to do things. In terms of the type of model for this, so I have it's a scale mean that ranges from 1 to 4. So it is bounded, but it's continuous in the middle. What I ended up looking at after I had built the full models was whether or not a conditional normal distribution seemed like a reasonable thing and whether any of the predicted outcomes went out of bounds. It seemed reasonable enough and none of the predicted outcomes went out of bounds, so I decided that I could just cheat my way into a general linear modeling analysis for this. Unfortunately, the options for generalized models in a multivariate framework are not as many. So like you don't have as many choices for flavors of binomial, for instance. So you're somewhat have fewer choices, at least in traditional software availability, if you're in a multivariate framework. So this is the analog to our very first unit, sort of focusing on general linear models just before we got into the generalized stuff. Now this is the multivariate version of that, and then we'll segue into multivariate generalized by the end of the class. So this is what the data set looks like. This is from SAS, but it would look the same. So in the original version of the data, which I call this either wide format or multivariate format, it's 1 row per family, because family is the unit that's being measured repeatedly. And so I have as separate columns the gender of the kid, the education of the kid, and the mom and the dad. And then these are the three outcomes that I am predicting. So for instance, in the first family here, the kid and the dad have the lowest possible score. So they're very unconservative, whereas mom's a little bit higher. And then in the second family, kid's still at the lowest end of the range, but dad is much higher. So some variability within and across families here. So the first thing that I have to do is take this data set and transpose it into something that looks like this. So I will show you the code on how to do that, but this is the end result. So I think it's helpful to visualize what the code is trying to do when you're looking at it. So now each family, as you can see by the ID number being repeated here, has 3 rows of data. Any of the original variables that you had are just repeated. And then I have this new categorical variable that is literally a string. I made it in SAS that way. So kid versus mom versus dad, and then I have my 3 dummy codes. So rather than naming these DVA, DVB, and DVC, I named them kid, mom, dad. So it's up to you what you name things, but it's always useful to name something that's intuitive to you so that when you come back to it, future you knows what you meant. And then marital is what I have called the generic Y column because it is all the same scale, but these are different people's responses to it. So conceptually, we're studying marital attitudes as the outcome variable from 3 different people. So the first part of this example, part 1, we're going to be using the long data set down here. For path analysis, we'll be using the wide one up here instead. Any questions so far? All right, moving along. So Stata has an option called reshape that I used to restructure the data. The only catch to it is that you have to have the variable that you want to create one column out of have a suffix pattern to its names. So in my original data set, this is what I called my outcomes: kid marital, mom marital, and dad marital. And Stata didn't know what to do with that. So I had to rename it marital 1, 2, 3, and it's like, oh, I get you now. And there may be ways to work around this, but after 30 minutes of Googling, I gave up and just renamed my variables. So keep that in mind, Stata users, that if you can name things in a way that's very predictable, that will be more advantageous. So then reshape long means I want to go from the wide per 1 row per family to 3 rows per family long. Marital is the name of the new column I'm creating out of these 3. And it knows that because of the name. So it basically took the front part of the variable name, stripped off the 1, 2, 3, and saved that as a column. So when I say I'd like to call it marital, it's looking for the original variables to have that as a part of it. I and J, damn it, Stata, don't do that to me. Family ID is how the original data were structured, and DV number is the new indicator variable to keep track of which row is which. Next step, creating the dummy codes. So I'm creating new variables that are all set to 0, and then systematically changing them over to 1 for each of the DVs, then making labels. And then I am removing missing predictor variables because any cases that don't have the gender for the adult child and the 3 levels of education for each person, if they're missing those, the whole family is going to get dropped because those are being used as family level predictors. So to prevent that from giving me different ends across my analyses, I am selecting complete cases with respect to my predictors. In R, I found a function in base R called reshape that seemed reasonably intuitive to use. I know the tidyverse will do things like that, but you know how I feel about that. I don't munge, and I don't tidy. So we have, what is the old data called? Which way do you want to go, long or wide? What is the variable called that is going to be your repeated thing that's sampled repeatedly? What are your original columns called? What do you want the new one to be called? And then time var, it's anticipating this to be longitudinal data, not multivariate data of another kind, but whatevs. I just have DB number, and it's going to be 1, 2, 3. Then I do the same set of dummy codes here, starting 1 for each person at 0, and then changing them to 1 if the DB number is each of those, and then subsetting just to cases that have the same complete predictors here. All right, any questions on syntax or the setup for this? All right. So part 1, multivariate general linear models via univariate software. We'll come back here. So what I'm going to show you is 2 different versions of an empty model, one with each of the parameterizations so that you can see what the code would look like. So 0, because we don't have anything in it yet, it's empty. A for the first version. This is the version that uses a general intercept. So first in Stata and then in R. Marital is the name of my new column that holds all 3 outcomes. I am putting in dummy codes for kid and mom. That means that dad is going to be my reference. Now, all this stuff is brand new relative to what you've seen before. The package that we're using is mixed in Stata, which does standard multi-level or mixed effects modeling for general outcomes. So this is conditionally normal stuff. Stata has a whole bunch of routines for multivariate and mixed model analysis for generalized models. They start with the name ME in front of it. Like if you wanted to do a binary outcome rather than logit, it would be ME logit. If you wanted to do an ordinal outcome, I think it's still, is it logit still? I don't remember. Point being, the names that we already know, stick ME on the front, and then you get the mixed effects version. So because this is set up to do multi-level modeling, the next piece in here, by the way, these three bars are line continuers. Stata doesn't know when you're done typing to it. You have to tell it that. So all of this is one line in terms of Stata's understanding of the model. What this is doing here is telling Stata how the multivariate data are structured, and it's by family ID. So it knows that that column is what unites the rows from the same family. The no constant here is shutting off a random intercept variance that gets estimated by default. So that is the workaround strategy we talked about last time with respect to how you can introduce correlation across your outcomes. I'm not using that in this model because I don't have to. Instead, I'm telling it for the residuals to make them unstructured and that the residuals are organized by DB number. So then it knows that every time it sees DB number 1, that that's the same kind of person for each type of family. When you are doing multivariate and mixed model analyses, degrees of freedom for the denominator are something that you can't easily figure out. It has to be estimated in most cases, and so this is the approach that I tend to use because it's common across programs. And these models for unstructured residuals can take a while. I recently discovered an option that I thought was really funny. If you just write the word difficult, seriously, this is a real option. I'm not making this up. If you write the word difficult, it somehow changes the under the hood estimation procedures and makes it go faster for certain kinds of models. Rather than learning which kinds work with it and which kinds don't, I was like, what if I put it on there? It seemed to help. So there are analyses that I've helped people with that literally take days to converge. And after adding this difficult, it took hours instead of days, which is an improvement. So several of you I noted on your homework 5 outlines to expect long times to run your models if you have very big data sets. So you might want to factor that into your plans when you're trying to run things, that they're not going to converge instantaneously if you have a very large data set. But then you can watch TV and feel productive. It's like, I'm working, see? Stata's chugging, and I'm catching up on Grey's Anatomy. What could be wrong with that? We call it multitasking. All right, asking it to spit out the -2 log likelihood, which I usually use for homework checking and for model comparisons. And then I am using linear combinations to get the intercepts for the alternative outcomes. So we start with the general intercept and add to it the effect of the kid dummy code. That gets me to the kid intercept. Do the same thing for mom. And then the only difference that I don't already get out of the model is kid versus mom as the non-reference DVs, and I can ask for their difference by making one of their slopes -1 and the other one 1. Okay. Questions on any of that?
What does the small mean?
Oh, the small, yeah, good question. So the default in Stata is to use, to not use denominator degrees of freedom for this mix models. That means that you would get z's and chi-squares for your test statistics. That's not going to be accurate in smaller samples. So this option switches it to give you t's and f's that are used Satterthwaite denominator degrees of freedom. And in order to have your linear combinations also have those t's and f's instead, you have to use this option small. You would think that if, because you asked for it in the model, that everything you asked for after the model would be consistent, and you would be wrong. You have to type it for every single one. Satterthwaite, by the way, is related to the idea of, it actually originated from dependent samples t-tests where the variances are different across the conditions. Like there's a particular way of addressing degrees of freedom in that is sort of borrowed and extended for this purpose. All right, so here's some output. So note that first thing it's telling you is how your data are organized. So I have 420 observations, but number of groups, meaning repeatedly sampled, repeatedly measured units, I have 140. So I would always like stop here and make sure that it understands your data structure, because if it doesn't, everything else is not going to work. It gives me a multivariate Wald test of the model. So this is the same thing that you would get in a standard linear regression. It's like the F test for the R-square of the model, same thing. This is the results of our model for the variance. And I have labeled these things for you because I'm nice. This is not Stata helping you, this is me. So when you get your output and it's not labeled, don't be sad. If the output came with interpretations baked in, I would not have a job. So, yay for that. So we have var E1, var E2, and var E3. Those are my residual variances per person, per type of repeated measure. These are unconditional because nothing is in the model yet. So this is all of the variability in marital attitudes to be predicted for each person. Note that these numbers look pretty similar, but whether or not we could constrain them to be equal and not hurt the model fit is an empirical question. I think it's better to err on the side of letting things be different, even if they could be the same, as opposed to forcing them to be the same when they really want to be different. Does that make sense? Like if these numbers were like 10, 1, and 5, and I tried to make them all the same, I might get something like 5, but that would be way too small for some outcomes and way too big for others. Here, it looks like 3, 3, 3, 2, 3, 2. Okay, maybe those could all be the same, but I'm not really hurting anything by letting them stay different. I might be losing a tiny bit of power. But the thing is that as we add stuff to the model, what if, for instance, education really matters in predicting the dad outcomes, but it doesn't really matter in predicting the mom outcomes? Well, then the amount of variability left over could vary by outcome type based on how good your model is for that outcome type. So just because they look the same now doesn't guarantee that they're going to stay the same as we build the model and explain variability. These are covariances. Question?
Where did the e's come from?
It's just what it calls it. Like the E at the end of the equation is residual variance. So do I have, yeah. So I have just the fixed effects here. What isn't being shown is that I would have like an E for the dad and E for the mom. And if I wanted to notate that, I would do the same like dummy code switch thing attached to each one of them.
Lisa?
Yeah.
Yeah, why are we using REML instead of ML?
Because REML's better.
Okay.
You know that. So REML, by the way, is a thing that we have not talked about in this class. It is maximum likelihood, The RE part stands for residual or restricted, depending on whose book you read. And the reason that I'm using it is because it operates similarly as ordinary least squares regression in that these variances are being estimated taking into account the number of fixed effects it took to get to that amount of variability left over. If you don't take into account the number of fixed effects, your variances would be potentially too small, which means that your standard errors would be too small and your p-values would be too small. At a sample size of 140 families, it probably wouldn't matter much, but this is sort of best practice if you have access to it. However, the reason that you have not heard about this much in this class is because for generalized models, REML is not a thing. It's not possible. Only in like pseudo approximate likelihood kinds of things, and we're not going to go there for this class. So this is just for the circumstance of a multivariate general linear model. So we got the covariances between. So this is the really important part. This is how we are building into the model our dependency. We are not assuming that these observations are independent. We are assuming that the three observations from each family are related. This is how related they are. We are assuming that families are independent, though. The highest level, so to speak, of analysis is always assumed independent. These are covariances. All I can tell is if it's positive, then as one goes up, the other goes up, but covariances are in units, and so I don't know what that means. So one of the things that I want to ask for is the correlation equivalent. So here are the 6 values organized into a matrix, makes it a little bit easier to follow. The diagonal is the variance of each type of outcome, and then the off diagonal is covariance, and then these are correlations. So it looks like before we do any prediction whatsoever, that the correlation between the outcomes from the kid and the mom is 0.13, the kid and the dad is 0.25, and the mom and the dad is 0.29. So it looks like the parents might have attitudes that are more aligned than with their child. Probably not too surprising. In R, we are using GLS from the NLME package. There are many ways to do multivariate and multi-level analyses in R, but only one that I know of, which is this one, that allows you to specify whatever patterns of correlation and heterogeneity of variance you want across your outcomes. So method equals REML is referring to the estimation type. Model equals, so this is where formula used to be. It's analogous. It's a little bit different than what you're used to seeing, but it's analogous. So model equals marital squiggle, and then the one, and then the kid and the mom. So the one is for the general intercept. The next 2 lines are how you address the structure of the variances and covariances. So correlation equals, that whole long thing, says, I'd like separate correlations for each pair, please. And how did I figure this out? I asked the Google, and I found someone's code, and this worked. So how do I do an unstructured R matrix in R? So thank you, Mr. Google. Or Miss Google, who knows? Weights, again, I never would have figured this out without help. This is how you get heterogeneous variances. So I'm allowing different variances for each type of outcome and different correlations between each pair, unstructured. Then I want it to print the -2 log likelihood and then give me the rest of the results here. So in contrast to SAS and in contrast to Stata, the output for R is organized very differently and frustratingly to me for these types of models with respect to the variance. So the first thing it gives you is the last thing we looked at in Stata, the correlations among the 3 outcomes. Okay, that's nice. Note that it's organized weirdly. It's not a symmetric correlation matrix. So like it's not 1, 2, 3, 1, 2, 3. It's off so that they're saving space. But if you're used to staring at correlation matrices that have the same rows and dimensions, it looks weird. So just keep an eye out for that. Then we get this thing, variance function structure, different standard deviations per stratum. And I get a 1 and then some numbers. And it took me a very long time to figure out what this was. But what it's doing is setting one of your outcomes as like a reference, and then these are multipliers to get to what the standard deviations would be of the other outcomes. I don't know who thought this would be useful to report this way, but they are incorrect. Then we get residual standard error and degrees of freedom. And I'm like, no, please. Can I just get the R and R core matrices? So yes, you can if you know how to ask for it. Get var cov means give me the matrix of variances and covariances, not the standard deviations. So then we get on the diagonal the variance for each kind of person that we saw before, covariances on the off diagonal, and then core matrix of one of the internal objects I found gives you the correlation version of it. So this is redundant with what shows up here, but I wanted to include it for completeness. Note that I had to add some things that are specific to this data set to make this work. So individual 3996 is the first family ID number in my data set. So in theory, if I had a model that somehow specified different variance estimates as a function of something, I might have to have more than one of these printed, but in this analysis, everybody is assumed to have the same structure. So you just need to grab one ID. Likewise, the 3 in the brackety brackets, can I make that term? Bracket with the bracket? It's a brackety bracket. That's because I have a 3 by 3 R matrix. So you change the number to however many dimensions you have that's consistent with however many outcomes you have. Then I wanted to recreate the omnibus F-test of the model, the multivariate Wald test for my two, currently just the 2 dummy codes that differentiate who's who. I wanted to recreate this in R. I'm like, okay, I know how to do that. So I used GLHT, and I did it this way in this analysis, where basically I said, can you lump together the mom slope and the kid slope? In order to get the right degrees of freedom, I had to feed it in manually. It didn't figure that out on its own. And then I get this result. Global test, chi-square. Wait, I don't want a chi-square. I wanted an F. And R said, nope. It threw an error message and said, I'm not going to give you the F. But then when I went into the object, it was there. Like, you just won't print it for me. Okay, I can fix this. So then I saved that result, found where it was. It's called fstat test df, and this thing was the p, or the degrees of freedom. That's numerator, denominator, and then this thing was the p-value. So I beat it. It's very funny to me that it told me it can't do it, but it actually did it. So I win. I'm not very good yet at figuring out how to find these things. So that's one thing, like, if any of you know how to do it better than me, like, I'd like help. Because I just navigate through the tree structure until I see the number that I think that I want. And that's how I figure it out, which is an inefficient process at best. But all the things are saved somewhere in there. To get the linear combinations that are not directly given, GLHT for that in the way that you're used to seeing. So this would be the kid-intercept. It's the reference DV plus the effective kid. This one's for the mom, and then this is the difference of kid and mom as the alternatives. So then here is output, and I printed it from SAS because it's organized so much more nicely of what we get from these things. So the model itself directly gives us 3. It's labeled intercept because this is a general intercept. So 1.95 applies to everyone's scores because this is the general intercept version. The effects for kid and mom are the mean differences for the other people. So on average, the kids are less conservative than the dads, and the moms are non-significantly less conservative than the dads. What I don't know is the kid versus mom, and so that's a linear combination that I asked for down here, the difference between those two along with what the actual means would be for each type of outcome. Okay. Questions so far? So that's the general way. Here's the alternative. This is the version that takes out the general intercept and replaces it with one for each person. So in terms of the code, first theta and then R, I've got now all three dummy codes in here. And the reason that I can have all three and not have it be redundant is this no constant on the first line. That kicks out the general intercept. So normally if we have like a 3-group predictor variable, and you want to put your 3-group predictor variable in the model, how many different dummy codes do you need to make if it's a 3-group predictor? You just need 2. The reason you only need 2 is because we have the intercept to cover the third. But if you kick out the intercept, then you need the third. So the first no constant, as I said in my comment here, removes the general fixed intercept. The second no constant removes the random intercept that we're not using because we're just letting the residuals be unstructured with heterogeneous variances instead. We're directly modeling the correlation between outcomes, not creating one through a workaround random intercept. So then as a consequence, the things that I would need to ask for in terms of linear combinations would be the differences between people, because the model is going to tell me what is the mean for each person. If I want to know if those means differ, I got to ask for it. Same thing if I want to know if there's an overall difference across the 3 types of outcomes in their means, I have to ask for that as well, because that isn't going to be given correctly otherwise. In R, see if you can spot the difference. Just in this part right here. Where'd it change? Right there. It's a 0, not a 1. So I took out the general beta 0 and I added that in here instead. So that means that this 0 is not a column that you have to keep track of. Like, it's just gone. Then otherwise, the code is exactly the same as before. I'm asking for the joint hypothesis test of the two differences across the 3 outcomes, fighting with R to get it to show it to me again, and then getting differences between people as linear combinations. And so then this version of the model, the output looks like this for what we get directly. Kid, mom, and dad. Those are the means for each. Mean differences across them are linear combinations given down below. So given that this, I think, is more intuitive, and given that this directly corresponds to the path models that follow, we're going to stick with this one. Okay, questions? Zoomers, you still with me? See how long? Oh, there's some thumbs. Delayed reaction. She's talking to me. Shit, gotta pay attention. Yes, I am. So I knew at this point that we might be a little tired. So rather than making you figure out what changed, I just put it in yellow. You good with that? Here's the new part. And by we, I mean me also being a little tired. So future Lisa would appreciate this, I thought. That's one of my new things. Think about what future Lisa would want and try to, arrange things to that. So we're adding the kid's gender as a predictor of each attitude. We already know what the gender is of the parents in this study because the data are organized into moms and dads as such discrete groups. But the adult child could be either one. So I added kid boy, meaning whether the child is a girl or a boy, and boy is the alternative group for each of these 3. So then in terms of the code, note that there are no main effects of gender here. Everything is attached to one of the DV dummy codes. It has to be, otherwise you're specifying something that you didn't intend. I then asked for, so this is going to directly tell me what is the effect of the child's gender on each person, and then down here I'm asking, are there differences in the effect of child gender across people? I'm also showing an example of how you can do other kinds of hypothesis tests. So one way to think about this data is 3 outcomes. Another way to think about it is parents versus children. So this is an example of how I would do a linear combination where I want to lump together the effects of a predictor on the mom and the dad and compare it to their kid. So note I've got a 1 and a 1 here. That sums to what? 2. See, I'm really, these are softballs today. So I have over here a -2 to balance that out. And then because I don't want the difference of slopes in units of 2, I take the whole thing and divide it in half. So now I'm back to the -1, 1 sort of idea. It's just that I've engineered it so that I can redefine how these things are grouped together. You can do anything you want with these. So just an example of like an alternative type of hypothesis test that you might want to try. In R, we've got the same pattern here. So I've still got kid, mom, dad. So we still have the intercept for each kind of person. And then I have my 3 what look like interactions but aren't really. It is the effect of gender on each person. That's what this is. So these are main effects from the perspective of how you would interpret them. They're just outcome-specific main effects. Switches is really how I would think about it. It's not an interaction term. All the same usual stuff, trying to get the R and R correlation matrices, trying to get the difference across the slopes that is hidden for me, and then these are the linear combinations, and this is what it would look like in R, at least as best as I could tell. So the same idea of lumping together the parents, but I'm giving them 1/2 directly in this case. So this is output from SAS because it's a lot shorter and neater to organize, but you get the same types of patterns in the software. That's online on the download folder, of course. Here's the variability left over and the covariability left over, correlations left over. Is there a difference as a function of the child's gender across the 3 outcomes? Nope. And if I go into the solution, then now the intercepts are all conditional. So these are from families where the adult child surveyed is a girl specifically. And then this is the effect of the child's gender on each person. Unsurprisingly, it's only significant for the person who it actually is. So whether you, as the adult child, are a man or a woman matters for your gender attitudes. Men have more conservative attitudes on average. But the gender of the adult child does not matter in predicting the mom and dad's outcomes, which makes sense because we don't know who else is in their family. Like they might have another child who is of the different gender. So I can't make any kind of conclusions about this. So I included it just to sort of say, yep, it's not significant and I'm going to take it out. So moving forward, then I don't have to have these slopes predict the other outcomes. I can leave it only for the kid. That's allowed. You can have slopes predict some outcomes and not others. So all of the combinations suggested that adding parents together doesn't change the story, so we'll leave that out. So then I'm adding my own education. So I have in the equation here, the only gender effect now is just for the kid, so B11. And now I have dad's education on dad outcome, kid's education on kid outcome, and mom's education on mom outcome. So own education predicting your own. Same pattern in terms of adding stuff to that. They look like interaction terms, but they're not. Here's the addition in R as well. Variance and covariance left over, correlation left over. And here are the new results. So we still have a significant gender effect on the kid. In terms of kid education, does not matter in predicting their own score. Mom's education does not matter in predicting her score, but dad's education does matter in predicting his score. Negative relationship here means the more educated dad is, the less conservative he is. Seems reasonable? So you might be asking, like, why did I do it this way as opposed to having one column that has education and it's person specific? The reason that I did it this way is to allow for the possibility that any of these could predict any of the other outcomes. So one of the things that was of interest when this study was being designed and collected was the effect of having a father who was more or less educated, and how that sort of propagated to the other people in the family. Like dad rules the roost kind of thing. These data are old. So here is allowing the effect of dad's education to predict the kid outcome, and allowing the effects of dad education to predict the mom outcome. So this is sort of like actor-partner sort of crossy stuff. So we add those terms, the same as usual. I made some pictures out of this model because this is the last model that I have for this part. So I generated in Stata a new variable that is the predicted values. I did that so I could check to make sure they all stayed in bounds. I also asked it to create standardized residuals, and I'm going to make a picture of those to check deviations from normality and stuff like that. So I saved those things. And I figured out how to do at least some of that in R, didn't I? Yeah, I did. Look at me. I made a histogram in R. Yay. I'm always proud of myself when I can make a picture. So, yes. So then we have, I also asked for all the differences in the effect of dad's education across 3 people. So these are getting bigger and uglier, but it's the same concepts that you already know how to do in terms of differences and slopes. So here's my model, again, repeated, so we can interpret it. Here are the new effects. So I left in controlling for your own education so that I could say after controlling for your own education, this is the incremental effect of having a dad that's more or less educated. And it looks like dad's education doesn't predict the kid's outcome. Dad's education doesn't predict the mom's outcome. So when I originally made this example, I was like, okay, I'm done. Can you think of anything that I might be missing as a possibility here that might make sense?
Mama.
Yeah, what about the mom? Don't moms matter? Turns out they do.
Yeah.
So I fit this model as a path model, and the fit was bad. I would not have known that the fit was bad. There's nothing in this that would tell me that. Because I am missing the effects of mom education on the dad and mom education on the kid. So it turns out once you add those, the fit does get better. So you'll have to stay tuned to see the exciting end of that part of the story. You'll have to come back next week when we do path models. In the meantime, here are some words. So model 0 through 3, describing what we've found and done thus far. Here's what it looks like in terms of looking at whether general linear models are a reasonable thing. So this is some residual plots out of SAS. This is lumping together all 3 outcomes, by the way, in that one column. Do you think that looks normal? It's like, it's not the worst thing I've ever seen. You know, it's a little bit wonky on the ends here. The variability looks maybe a little bigger in the middle, but not horrible. All the predicted values stayed within bounds. So I'm saying, yeah, so situations like this in which it's like, it's probably fine. This is where we might find alternative ways to compute standard errors that would be more robust to deviations from normality. So one option might be bootstrapping or jackknifing, those kinds of resampling things. Stata has something called robust standard errors. And in path models, we're going to use what is known as robust maximum likelihood estimation, which corrects standard errors and fit statistics for deviations of multivariate non-normality. So for situations in which it's like, this could be okay, but I just want to be sure, adding robust standard errors is a reasonable thing to do. I don't think this calls for a generalized model because it doesn't look like it's an egregious violation. And I'm not sure what I would do, to be honest, because in path models, there's not binomial options most of the time. So where we are headed, the second half of this example, very, very much code, is this model. Have you seen pictures like this before? This is a path model. In these models, each box is a column in your data set. So this is in a wide data set where each of these boxes is a separate column and it's 1 row per family. Typically, you show predictors to the left and outcomes to the right, or predictors to the top and outcomes are on the bottom. at least in when articles written in English, because we read from left to right. It might be different in other languages. And I have used different types of errors to sort of convey different things. So like these are child effects, the solid lines are mother effects, and the dashed lines are father effects. So you can use formatting to make your pictures look less overwhelming. This is where we're eventually going to end up. Mother's education is going to be a predictor of all three of them. Father's education, all three of them. Child's education, only this one. So I will show you how to start doing those next week. Question?
Yeah, can you remind me of what's the difference between past model and the one we just talked about, other the estimator,
In terms of the model and what the parameters mean, there is literally no difference. The difference is in how you are estimating those parameters.
this one is the maximum.
This is the end result after I add in slopes for mother, but I did that in, here let me find, I did that in the same thing. So other than switching to, and so I switched some of the estimation options to be the same too. But no, there is no difference. This type of analysis, because in this model, every variable is either a predictor or an outcome, and I'm just letting these boxes be correlated. That's not in the picture. I probably should put it in the picture, but it's hard to make curved arrows in Word. Because each box is either a predictor or an outcome, and the outcomes don't predict each other, they're just correlated, you can do this kind of model as a path model, or you can trick univariate software into doing it for you. But if I had, say, child attitudes and I wanted to put an arrow to mom attitudes, that's where it breaks. Then you can't do it in univariate software, because child attitudes would be both a predictor and an outcome at the same time. And univariate software only lets you predict one column, not multiple. So this is a truly multivariate analysis at this point. It's called a path model if all the variables are observed. If you see one that has circles in it with latent variables, then that's a structural equation model instead.
So the only difference is this is a truly multivariate model?
Yes, I call this truly multivariate with quotes around it, yes.
So the other one, we just tricked the
Yes.
them to do that for us.
Yeah, we tricked univariate into doing multivariate, which can be done for certain types of things, but not for everything. So, all right, other questions? Then I will let you know when stuff is ready for next week. We're going to start talking about path models. Woohoo! Let me know if you need help with your homework, and I hope to get everything turned in on Monday for everyone so I can start grading. Thanks for being here. See you next week. Have good weekends. Take care of yourselves.